Hello everybody, in this lecture we will be going over 2017 USAMO problem number 3. This problem was proposed by Evan Chan. Here's a view of this problem. Triangle ABC has circumcircle omega and in center I, and then we extend ray AI to meet side BC at point D and also the circumcircle at point M. Notice that M is the midpoint of arc, minor arc BC. And then we will go ahead and draw a new circle with diameter dm, and that circle will intersect with the circumcircle of ABC at the point K, at which point we will go ahead and extend the line MK to meet BC at the point S. So that's the next point. Finally, we will draw SI and call N as the midpoint of that line segment. The claim of the problem is that the circumcircle of this KID and the circumcircle of MAN, they will obviously meet in 2 points, which we call as L1 and L2, and then the problem suggests that the midpoint of either IL1 or IL2 happens to be on the circumcircle of triangle ABC. So we'll solve this problem in multiple steps. Probably, I think I did use 7 or 8 steps to show it. So my proof will follow very closely with the post on AOPS by Evan Chan. I did some minor changes to the proof, but the notation will be pretty similar. So you can also follow the text from Evan Chan's post on AOPS. So let's begin by first drawing a perpendicular from point M to the line BC. So if I draw the perpendicular, it will obviously meet also the meet also the circumcircle of with diameter dm. The reason is that a 90-degree angle here will subtend the diameter dm. So I call this point as W, but then I go ahead and extend this line as well. So all the way to the other side, diametrically opposite point, which I call it as X. Okay, so and let me remind you that this angle here is 90 degrees. So DW and WM, they meet at a 90-degree angle. So secondly, we will draw KD, line KD. Again, this is another 90-degree angle here. Angle MKD is 90 degrees. Extended, I claim it should meet the point X. The reason, again, obviously XM is the diameter of our circumcircle of ABC. As a result, KD extended should meet the circumcircle at the point X, because that 90-degree angle MKD is equal to angle MKX, which subtends the diameter. Now, thirdly, this is where things start getting interesting. If I extend XA, so I claim that it will meet the point S, and the reason is very simple. If you focus on a triangle XSM, on that triangle XSM, obviously D is the orthocenter. Why is that? Because XK is an altitude, as is SW on that triangle XSM. As a result, the third altitude, which obviously should go through that orthocenter D, so will be MD, and well, this line is obviously the ray AI, right? So it will eventually hit the point A, right? And nicely, this A will have this 90-degree angle as we know it, because it subtends the diameter XM. So it is obvious then that these 3 points are collinear, and D is the orthocenter of triangle XSM. Okay, in the next step, we will make use of the in-center, x-center lemma, which was again popularized by Evan Chen. So notice that the AX center of triangle ABC will lie on the ray AI, right? So M would be the center of a circle, which will go through I, B, and C, but it will also go through the AX center of triangle ABC. So this is a very well-known result, which is, as I said, usually referred to as the in-center x-center lemma. Due to this lemma, we know that MB is equal to MI, which is equal to MC, which is equal to MIA. So M is the midpoint of the diameter IA of that circle, of that dotted circle that I just did draw. So that's perfect. So in the next step, what I'm doing is I would like to draw the line XIA, and then I would like to drop an altitude from I to that line. So let me go ahead and draw that line. So a line probably something like that. So that's XIA. If I drop an altitude from I to that line XIA, obviously it will subtend the diameter of that dotted circle. So it will happen to be somewhere on that dotted circle, right? So let me put it here. But it's not necessarily on the line AC, right? Not necessarily on side AC of our triangle, but definitely on the circle. So something like that. This is 90 degrees, and I will call this point as E, along with the same notation of Evan Chan's solution. So then I have the following claim, obviously, right? So that S, I, and E, I claim will be collinear. So let's try to see why that's the case, right? So right now it's not obvious why S, I, and E would be collinear, but that's my claim. So consider the circle with diameter xi. So this circle will definitely go through the points A and E. So that circle here, let me go ahead and probably just kind of sketch that circle. If you see this circle here, so that circle has diameter Ix, and notice that, so let's call it, let me call this circle with center M as W, and let's call this new circle as, I don't know, gamma maybe. So notice that the lines I claim XA, EI, and CB will all meet at the same point at the radical center S. Why would that be? Because look at these three circles, and consider circles little omega, capital omega, and gamma. The radical center of these three circles, so what is the radical axis between the two omegas? The radical axis between the two omegas is BC, right? So that would be BC. The radical axis between capital omega, the circumcircle, and gamma would be AX. So this one is AX. Finally, not this one, sorry. Finally, the radical axis between this circle, little omega, and gamma would be IE. So this one is IE. So therefore, these three lines should meet, right? So BC intersection AX intersection IE, and there's only one candidate. We already know that XA and BC meet at S, so therefore IE also should meet at S. So therefore, this implies that S, I, and E are collinear actually. And as a result, now the point I, the in-center of triangle ABC, has a new role now, right? I happens to be also the orthocenter of triangle XSIA, and let me go ahead and draw the line SIA like that. So I claim that I is the orthocenter. In fact, if I extend this, obviously it would make a 90-degree angle here because it goes through the orthocenter. But more importantly, IIA is the diameter of this dotted circle, little omega. So as a result, it will also meet this dotted circle as well. And let me go ahead and call this point as L. Now we're almost done with this problem. I claim that L is one of these 2 points, L1, L2. So how can we show that? So let's first show that L is on the circumcircle of triangle MAN, and then I'll also show that L is on the circumcircle of triangle KID as well. But let's start with the first one. So why would L be on the circumcircle of triangle MAN? For a very simple reason, from the fact that in fact MAN, the circumcircle of MAN, is in fact the 9-point circle of triangle XSIA. So I want you to sit back and think for a while why that's the case. Let me elaborate. Remember that I was the orthocenter. Remember the orthocenter of XSIA, and look at from a vertex of this triangle to the orthocenter, the midpoint is N. N is the midpoint here, so that's one of the points of the 9-point circle. A is another point. A is the foot of an altitude, and so 2 of our points are there. How about M? Look at the point M. M is midpoint between I and IA, right? A vertex now on that triangle XSIA, and I, which is the orthocenter. So it's perfect. So this is the remaining point that uniquely defines that 9-point circle, right? So we have 3 of the 9-point circle, so that defines the 9-point circle, and the 9-point circle will definitely go through the foot of the remaining altitudes as well. L is one of them, obviously. E is another one, so that 9-point circle will go through these points. So let me write that down. So because 9-point circle which goes through the points M, E, A, and obviously L as well. So this part is easy. Now the second part, why is L on the circumcircle of KID? We can show this very simply by looking at the power of a point argument. Notice that ASKD is cyclic. Do you see why? ASKD, because the angle DAS and angle SKD, they add up to 180 degrees, right? So they are supplementary angles, both being 90-degree angles. So as a result, if I apply the power of a point S, I realize that XA times the power of point X with respect to that circle, so XA times XS would be equal to XD times XK. XD times XK. But in a similar way, you can also observe that quadrilateral ASLI is also cyclic from a very similar reason, right? So notice that angle A is a 90-degree angle here again, SL is again 90-degree angle, and I. So you have a quadrilateral which is cyclic because angle IAS and angle SLI, they add up to 180 degrees. Again, the power of point X with respect to that new circle will give me XA times XS is equal to XI times XL. Now if I combine these two results, I realize that the left hand sides are equal, so therefore the right hand sides should also be equal, suggesting that XD times XK is equal to XI times XL, immediately implying by the converse of the power of a point theorem that in fact DKIL is cyclic. So therefore L is sure enough on the circumcircle of KID. Okay, so finally we need to show that the midpoint of IL happens to be on the circumcircle. So let's use phantom points. Let's assume that it is somewhere else, right? So it's not exactly on the circumcircle, it's anywhere else. So let's call this point as I don't know, the midpoint Q. I think we didn't use the letter Q. So because it's the midpoint, so IQ is equal to QL, and because I am is equal to MIA, it is obvious that QM is parallel to LIA. But if that's the case, so let me draw that. Okay, so my pen is refusing to write. Okay, so if QM is parallel to LIA, it means this is a 90-degree angle. But wait, IM, if that's a 90-degree angle, then Q better be on the circumcircle of triangle ABC, because look at this 90-degree angle here that we just identified. MQI, which is 90 degrees, is also equal to MQX, because XIQ are collinear. So MQX subtends the diameter XM again. So actually Q has to be on the circumcircle. So let me revise my drawing, I guess. Let me just delete it a little bit. So in fact, the midpoint of LI has to be on the circumcircle. So if I did revise the thing, and actually this also finishes the proof too, right? So the midpoint, so let's call it T. I think Evan Chan called it T in his notes. So T here, and perfect. So you have line TM. It's not going through K, obviously. Sorry for the thing, the drawing is not very clear, but it is obvious that that midpoint T has to be on the circumcircle, as we just mentioned, because TM is parallel to LIA, and as a result MTI is 90 degrees, but that's also equal to MTX, but angle MTX subtends the diameter, so as a result it has to be, T has to be on the circumcircle, and this proves the problem. Hope to see you guys in our next video.